Well, they were like, saying today, I don't know to get down there and say it's break, and I'm like laughing. Yeah.
Actually, I took it.
How are you? So you're doing coffee? Yeah. And you're in this class? You finish that?
I like the double E's.
Okay, so that was where I was here. I was because I like the easy side more than coffee more. I was like taking data structures, and halfway through the semester I was like, you know what, I don't need to be here. And then switched to my major. I didn't. Are you learning out? Are you learning out? Yeah.
I mean, I go.
I go.
Heading here, like about.
Yeah. I was already on campus. I think my Fridays were full, so I was already on campus. So I just sit in the library and do homework instead. So either sit in the library and do homework or sit in that class and do homework.
Yeah, okay, that's what I do.
Next Friday though.
I'm gonna have to study hard for it. Honestly, she's energetic, she's a good teacher. I just can't do it. So,
Well, I think that's the problem. Because she seems really nice, but just I can't sit there with. Yeah. I took it last semester and then dropped it for 2 weeks ago. This is too much. And I took it with Runyon, and like he did it so much better. And I'm not even sure, but that was the only way I learned it.
that's fair.
So you're doing electromechanics?
Just this one. I'm actually shadowing the
Wanted to simplify it, just for machines working, okay, we leave
So,
it.
are you?
I'm in both, but I'm
So for like these unique power, just like the numbers, like the back magnitudes of like the power voltage for it.
Five.
Okay, that's. Alright, but I have like coach of negative one, negative start ID.
Yeah. They do more like transmission lines and whatnot.
With Terry to. So.
Yeah, I know. They are aware.
What was that?
I made them aware.
Okay, cool. Thank you.
And the homework
For tonight?
or well Monday.
I'm doing with
Oh,
tonight.
that's Thursday.
I've been. Last week I was out there.
Yeah. It was a constant battle between me and my bed.
Yeah, yeah.
Hard to get through homework.
I think I've done. The last
You'll want to try.
Yep, so right after this, I'm going to do work on it.
Okay,
And then I got really about
that's true. It's not as good.
9.5 hours, and then Thursday, probably get back to there.
Okay, let's start. So, last time we were working on the ideal transformers. Can someone remind us about that? What's the good thing about an ideal transformer? And we finished up by solving an example pretty fast. So I think this is an important topic, so I'll go through that today again a little bit. But as a reminder, what's special about the ideal transformer?
Losses.
What do we do with the losses? Are they more or less in an ideal transformer?
You have less losses.
Definitely. We are actually avoiding the losses or ignoring them. So this is a very good simplification for calculations. Actually, the reason behind that is that at most, those losses won't count more than 5%. If you get a real transformer and you make the exact calculations with all the complicated stuff, you might save 3%, 4%, at most 5%. So there's a major research now in the improvement of the materials quality of the transformers so that we totally ignore even those losses. There'll be no loss at all, or it might be very tiny so that it could be ignored. So for now, we'll go over this simple example again. We made a lot of explanations, a lot of formulas last time. And we've seen in this example how typically we have the questions. So you'll not be required to make all those derivations in the exam. I'm going through derivations in those couple chapters because I feel that we have time. And I'd like people to know why we are solving this thing in this way. But that does not mean in the exam or in the homework you need to make all those derivations. If you know the rule, you can immediately use it, okay? So we had a single phase, two winding transformer rated at 20 kVA. So what's the 20 kVA? It's the S value. This could be called like the rating of this transformer. So if I go to the store, or if I look at Amazon today, and I need some transformer, I would look for the rating of the transformer. This is the typical complex power utilized by this transformer. So it depends on my application. If I need the 100 kVA transformer, it's not a wise decision to go and buy a 20 kVA one. So it should be around the needed or the supply or the load that I have. So anyhow, typically a reading of the transformer would include also the ratings of the voltages. So 480, 120 means that typically this transformer is being fed 480 volts at its primary side, and at the delivery side we'll have 120 volts. This is the ideal situation. So we can calculate the turns ratio from that. How much that would be? 4? Okay. So you simply divide those two values and you get 4. This will be the proportion of the input to the output voltage and the output current to the input current. Okay? What about the ratios of the impedances? Z. Is it 4? From both sides of the transformer, if I'd like to refer an impedance from one side to another, should I also use 4? Okay, good. It should be squared. I think we went over that because we were dividing both voltage equations, so we came out with a doubled impedance ratio. Okay, this is important to remember. Then I think this is everything we have from the primary side. I call it primary. They say here is the generator side. So from the other side, we can see that we have a load which is being connected to the 120 volts side, and it's absorbing 15 kVAs at 0.8 power factor lagging. Okay, so what's this information? So typically when you have any problem to solve anywhere, you should put your inputs here, or let's say the given information from the question. And what we did now, some brief calculations quite reflect what would be used later, okay? So it's important to know what are those values. So what's the 15 kVA and 0.8 power factor? How can I utilize them in my solution? Can we remember this representation from the previous chapter? We need to obtain those values immediately because we will need them for, I need to remind the people for the equation of S. What's S? What? I can't hear you.
P plus JQ.
Okay, great. Another representation of S. How can I calculate S? Okay, great. So typically here you'll be asked about currents and voltages. So those two are very important, or powers. I think now the question is solved. The other parts, A, B, C, D, are just going over all those equations. So how can I get the angle from the power factor here? Okay, we're done. So you just fill in those values here. You have the primary voltage. You can actually, he gave you here the secondary voltage, which is 118. I should give you either one, either at the primary side or the secondary side, so that you calculate the other. So here he gave you V2 equal to 118. Okay? There's something interesting. Can you compare this value with the ratings? How does it seem to be? Lower. This is a good thing, actually. We don't have to work at the full capacity of the transformer. So here we will have a ratio. So V1 will not be equal to 480. Even though this transformer is capable of transforming voltage up to 480. Okay? It's not a rule that my calculations in the question must be 480 and 120 volts, otherwise they'll be wrong. No, we're not operating at the full range. So he's asking us, I think this is everything we have in the given, in the instructions, and now we start solving questions. We need to calculate. He assumed that the transformer is ideal. So he simplified 50% of the problem, or even more. We'll see that later. And then we need to calculate the voltage in the primary side. He wants this V1. He wants the load impedance. Let's call it Z1. He wants the, He wants the load impedance referred to the 480 volt winding. Since the load is at the secondary side, I'll call it Z2, not Z1. Okay? So that people don't get lost. But in the second question, he said, I want the load impedance referred to the 480 volt. That does not mean I'm looking for Z1. I'm still looking for Z2, but referred to the primary side. So this is part C. Okay? Do you know what referred means? People who took maybe electromechanics know. What does that mean when I take something referred to another side? I understand, yeah, but what's the physical meaning if I refer something to one?
I step down or step up.
Okay, good, but what does it mean? It's the same value as seen from the other section of the circuit. And it will be scaled according to the ratio. It might go up, it might go down, depending on the AT. Okay, this is referring. I'm trying to observe this component from the other side. I will not see it as it is. So if it was Z, it won't be Z. Unless the transformation ratio AT is equal to 1. Okay? I think this is some side information, but it's good to know. If AT was less than 1, the scaling, it will get smaller actually from the other side. If it's more than 1, it might get bigger or inverse. So referring in simple words is just that how I try to visualize a component from the other side of the circuit. You'll not observe a component from the same side. You're looking into foreign components, typically. So it could actually happen in both directions. So sometimes they would say refer from the secondary side, then you convert everything from the primary to the secondary. But here he's saying, I want that from the other one, okay? And then the real and reactive power supplied to the 480 winding. So we have some information about S, but that S value, I think it's for the primary or to the secondary side, to the 480 or 120. This one here, 15, 0.8. Is that S1 or S2? Okay. But he's asking some information. I think it's related to the 480, which is S1. Can we relate that to S2? So how I get to S1 from S2? Okay, great. Don't put a ratio here. The power will be still the same from both sides. I'm just playing with the voltages and currents. Okay? This is a big mistake if you multiply by an A here. So I think here we're done now. we go through the calculations. Here he calls V2 E2. I have 80. I calculated that to be 4. E1 came out to be 472 expected, less than 480. I don't want to see 500 here. It cannot be larger than the rating for this case. And then here he put S2 in its form. He took those 15,000s here. He calculated the power factor. It came out to cosine inverse of that. It came out to be 36.87. And then he used the SVI star. He has the E2, which is V2. He has S2. He calculated I2 out of that. So now I got I2. And then how I calculate Z2, I just divide E2 by I2. That would be the value of the impedance. Part C, calculate the load impedance referred to the primary winding. So I'm seeing it from the primary side. I use the normal AT value squared. So I multiplied that by 4 squared. And then he's asking about P1 and the Q1. I just say S1 is equal to S2. And this is how I change the form. I think you're asking something related to that. So you need to transform this to those values, or do the cosine and sine of this angle and multiply it by 15,000, so you get those. And then you say, okay, those should be the same. So P1 is equal to this value and Q1 is equal to this value. And the question is over. So I thought that this question is really good. So I hope that you understood that very well. And it was really trying at home to see if you really know what's going on. There's one more note in this section. Here there's a special case of a transformer. I'd like you to look at that thing and to see what's quite special about it, about that representation. Is there anything special about it? Actually, this is here. It's a good case where they are both in phase. When you see the dots are on the same side, I think you are aware of that from electric circuits. This is a good case. They are in phase. It means that both sides are in phase. But if the dot was here, those are out of phase. So this is not an issue here. The interesting thing is here, the ratio. We rarely see, or we never see most of the time, a complex number in the ratio, because I typically cannot say V1 over V2 is equal to 1 plus J over 2. We don't typically use that in a transformer. But here, he just put the exponential here to reflect that the magnitude ratio here is, how much is the magnitude ratio? 80. Forget about this E. How much is 80 right now? MSU people, you can share. I keep looking at this to make sure you are connected. Nathan, you can share in the discussion. If you don't interrupt me, I won't see your chats here, because I'm opening the book PDF. Okay. So 80 here is 1, actually. I'm not transforming the magnitude. So if I had 120 volts on the primary side, I'll have 120 on the other side of the transformer. The change which is happening is on the angle. This phi here represents that I'm shifting the angle, actually, by that rate. Let's say it's 30, 40, whatever. And this is actually very important, because the complicated thing or the hard thing in this chapter is related to the phase shift of transformers. And we'll see that mainly in the three-phase transformers, and things really get bad there. Very bad. Very complicated, actually. So in this chapter, we'll try to do it in some simplified way, but normally transformers cause a lot of phase shifting also, not only magnitude change. So that ideal case also, not only we have no losses, also we don't have any phase shift. But typically you will have here this phase shift and it would affect the voltage and the currents in this circuit. Still, S will be the same. So here he made the calculations to show us that S1 will be still is equal to S2 and Z prime will be equal to AT squared Z2. So the impedance won't change because we know that the angle does not affect it in any way, okay? We are more concerned about the angle here. So this was a nice note here before we move into the real equivalent circuits for practical transformers. So here I would like to go over a few notes that what would change in this case, okay? So here in a practical transformer or real transformer, the windings would have resistance. Before we said they don't have resistance. The core permeability mu c is finite. Before it was infinite. It was very large, infinity. Now it's still large, but not a million or a billion. It could be like 1,000 or 200 or whatever. And the magnetic flux, which is B, is not entirely confined to the core. At first, I think I stressed last time that the flux is within that core material of the magnet. But here we see a section of it going outside somewhere. And there are real and reactive power losses in the core. Also, we've said before that the core itself is lossless. So it was quite perfect. So here we have a wide range of losses here and there, actually, and dissipation of flux. So the circuit will change a little bit. And we'll see now how complicated would be the calculations at this moment. So let's discuss this circuit. Any additions you can see? What are the additions? Yeah.
Series inductance and resistance.
Series inductances and resistances, yeah. We see that. Now each side has its own set of R and X, which is quite a good representation because those are some windings, they have reactance, and definitely they have some resistance. So this is good observation. What's new else?
Shunt branches there now.
Okay, very good. We have couple shunt branches. They seem to be at the primary side, actually, not at the secondary. And are they the same or different? Same nature? Both resistances, both reactances. So they seem to be quite different, actually, because of that J. And we see a few more currents being involved. I see IC, IM, IE. We see I2 being referred. This is not new. We just referred the I2 here at the secondary side. If we would like to take it to the primary side before the transformer, we have to multiply by N2 by N1. Okay? Which is 1 over AT. N2 is 1 over AT. Okay? Very common mistake in the assignments or exams that people think those two are the same. This is AT. Okay? If you reverse the thing, so instead of 1 over 10, it will be 10. Big change in calculations. Okay? So So I think those are our observations for now. We'll go over each component, I think, to see what has changed. So let me make a few more notes before we go to the text to make people understand what has changed here. So I'm very bad in drawing, but I'll try my best here. Should be like that. Anyhow. So this is V1 being applied here. This is V2 being tested here. This is I1. This is I2. Okay. This is the magnet. This is what we have seen before, and its representation looks like a transformer. So when I start to apply voltage, a current starts to traverse through the first winding, and that would lead, by the laws of electromagnetics, to a flux to be generated, and that will start traversing here within the magnet. Okay? That's not an instantaneous process. It's not like a switch of a lamp. It will take some time. Okay? Because this is a magnetic material here. So after some time, you'll be, it's like the gas pedal. You'll be increasing the voltage. You keep increasing the voltage, more current being generated. And then the flux is increasing within the magnetic material. So we would see some voltage being induced from the other side of the winding. Okay? And then we start to see a current being generated on winding 2. Typically, R1 and JX1 relate to this winding here. And R2, X2 belong to this winding there. IC and IM are here. And they add up to be called IE. So this value N2 by N1 times I2 is just the multiplication factor to make some of my calculations being easier. Because here I need to know that IE is called the excitation current. It's equal to I core, which is the current traveling through the core, plus the magnetization current. Okay? And I1 would be equal to IE plus I2 times N2 over N1. If you miss this term, this is wrong. Okay? You have to multiply by N2 by N1 to get it from that side to this one. So we understand why we have a resistance and reactance for the wires, because every wire has those values. It's not of capacitive nature. But what about the magnetic material? Why does it have IC and IM? IC relates to the core loss, which is typically like the hysteresis effect, which we'll talk about later. It relates to the magnetic material itself, because magnets do not act in the same way like other materials. So if I apply a voltage there, let's say this voltage, and I stay standing for a little bit of time, that voltage will induce certain current and some flux, and then it will dissipate back forth. But it won't take the same path. This is called hysteresis effect or hysteresis loss. By nature, the magnetic material will not follow the same path. It will go back from another way if it gets back to zero. Okay? Magnetization relates to the issue of the initiation of flux in the magnetic material. And typically, that tends to be a little transient effect. So if we add up those two losses, they will make up the excitation current in the transformer. And this will be small percentage of the total current of I1. So typically, if I'd like to calculate the efficiency of this transformer, I would calculate IE over I1 to see how much that would be. It should be less than 5%. If more than that is being consumed by the magnetization process or the core losses by the transformer, that means that the transformer is not functioning in the right way, or there's some issues with the magnetic material itself. So let's go over the details here. I think we explained about the resistance. They make that loss Ri squared. We have the reactance. We call it leakage reactance. It's also included in series. And here we'll get back to the equation. Previously, we said that I1 minus N2 over N1 times I2 is equal to RC divided by N1 phi C. Actually, there's something. Here he divided by N1, but initially we did not divide by that. This is what we had last time, if people remember. Okay? And we said that this term could be 0 in the ideal case, so N1 I1 would be equal to N2 I2. Now this is a different story. This is no longer 0. It has a value. Okay? This is the reluctance of the core. So here he made, if we look into the text, he made a simplification. He divided by N1 on both sides. And then he started to play with the terms here with the phi C term, which has some relationship with the induced voltage or the initial voltage at the primary side. So you get back to the equations, you substitute that by E1 over J omega N1. And we'll figure out this is a new representation of the difference of the both currents. It will be equal to that value. Okay? So defining the term on the right side to be IM, it's called magnetization current. And it's evident that IM lags E1 by 90. Definitely because it's of some type of reactance, it must lag the resistive currents or the currents of resistive nature or flowing through a resistor. And we've went through that in the previous chapter. So this is 90 degrees is showing up because of that J. And it could be represented by a shunt inductor of susceptance Bm equal to RC over omega N1 squared. That Moho's value is just 1 over ohm. Okay? So it's the inverse of every resistive value. They call it susceptance. However, in reality, there's an additional shunt branch, which is JC. It's called, it's a resistor with conductance, which carries the current IC, which is called the core loss. IC is in phase with E1 because it passes through a resistive component. Okay? This is IC. Let me get back to the figure so that people could see. Here. This is IC. This is IM. One is passing through a resistive component. One is passing through this component of having that reactance. So when you include those two, I think I've explained this equation here of the currents. The difference of both currents would be IC plus IM, which is the loss. And if you go deeper, it will be multiplying the voltage by this susceptance. Okay? So in a typical question, as we'll see later, we'll have to calculate those values. GC, BM, currents, voltages, IM, IC. Then I calculate I2, calculate I1, prove that everything is in order. So now we get into the section where I need to make some calculations to obtain those values, JC and BM, okay, of those shunt branches. There's no direct way to do it. So we need to do some elementary measurements called short circuit and open circuit analysis to figure out those values. This is the only way to do it. It cannot be determined like arbitrary. Just say I'll put 10 there. Okay. I hope people would remember the short circuit test and the open circuit test. Did you try them before in electric circuits? Did you do them in the lab and make all those measurements? Okay, I remember when I did them when I was undergrad. So anyhow, typically here he will start with those tests and saying when we have the winding 2 open, which means I2 is equal to 0, and we apply a sinusoidal voltage on the winding 1, then an I1 will be traversing in the first side of the circuit. So I1 would give us IC and IM. And here he makes all those calculations with I.
Dr. Sleeman, your audio cutting in.
What about now?
That's better, thank you.
Okay, great. So I was just saying that here there's something related to that in IC. There's a very little component which is eddy current. Can anyone remind us what about eddy currents? What are they? Why do they happen actually? Yeah.
Like the magnetic fluxes.
Where does the current go? If I have this wire here. This is a transmission line. You have a number of wires inside. They are bundled. I'm very bad in drawing, but anyhow. Where's usually the current is flowing? Okay. The current will be flowing on the peripheral, on those sides. Actually, most of the time, this inner component will be empty. This is by nature how the current flow. So this is the issue with eddy currents. So you'll see a hollow cylinder in the transmission line, and the current actually is being flowing on the edges of the component. This is a real challenge. So now, definitely not those wires, but they did a lot. So instead of having a single wire now, they put multiple wires inside, and they made them like spiraling like that above each other, and they decrease a lot their width. They make them as small as possible to ensure that there's all the current is moving without having that extreme area, because it's not being utilized. 90%, 95% of the wire cross-sectional area won't be utilized, okay? So everything will be flowing through those little sections on the edges, and that causes the loss. So it'll be actually a huge loss for the material. So most, I'm not sure if in this course or not. I think maybe in transmission we'll talk a little bit about that. Yeah, we'll talk a little bit about that when we talk about the design of transmission lines. So hysteresis loss occurs because of a cyclic variation of flux within the core, which requires the energy dissipated as heat. As such, hysteresis could be reduced by use of special high-grade alloy steel material. So we talked about what happened during those cycles, those variations. They are not the same. Eddy current occurs because of the induced current called eddy currents flow within the magnetic material are perpendicular to the flux. As such, eddy current could be reduced by constructing a core with laminated sheets of alloy steel. So associated with IM is a reactive power loss, which is of this value. The reactive power is required to magnetize the core. So IC plus IM is called the exciting current. So this is typically what we are saying. The sum of all those two currents, each of different resource, would add up to be the exciting current, IE. So here I think we covered everything in this curve, in this figure. So I can see here too the other representations actually. or three. In the first one, we referred even the secondary windings R2 and X2 to the primary side. So everything came out to be now on the primary side of the circuit. Can you see that? There's nothing on the secondary. In the second case, we removed this shunt branches. It's a single branch of two components. So anyhow, we minimized the circuit a little bit, so we ignored the exciting current, and that would make the calculations quite easier. In the best case, we removed actually the exciting current and the I squared R winding loss. So we said that it seems to be that the resistive losses are very little, so we ignored them, but we kept the capacitive or the reactance loss, because if you make some calculations, it seems to be that the inductor type loss is much bigger than the resistive loss. So that's why they made this approximation. Which one to use depending on the question? I would determine the structure and you proceed with the calculations. So first one seems to be the most hard one to do. The second one is quite simplified. The third one is very easy to calculate. Okay. So he's saying that the shunt branch is omitted. When it's omitted, it corresponds to neglecting the exciting current, since the exciting current is usually less than 5% of the rated current. Neglecting its power in some studies could be valid. While if we have a very high ratings, like 500 kVA or 10,000 or so, that 5% would count much more now. So we have an example to solve now. A single phase, two winding transformers rated at 20 kVA. I think those are the same ratings. So we'd like to do here some short circuit and open circuit tests to determine those values, okay, of the representation of the transformer. So he made a short circuit test and he applied a rated current at rated frequency applied to the primary side, which is denoted by winding 1, while the second side was shorted. So we could see here, this is in the case of short circuit analysis. He got a wire. He joined the connections here from the secondary side. From the primary side, he put certain voltage source. And then he'll make some measurements to see how much the current would be circulating in that circuit. And he neglected definitely the shunt values or branches. For the second case, he made an open circuit test. So he kept the primary side open. He applied now a voltage source on the secondary side, and he went backward. And he made calculations to determine I2 and consequently those values JC and BM. So let's see what's needed in this question. So I said about open circuit, short circuit tests. Now he got some readings. I think from the short circuit test, he got V1 to be 35 volts and P1 to be 300 watts. During open circuit test, he got I2 to be 12 amperes and P2 to be 200. From the short circuit test, determine the equivalent series impedance Z equivalent equal R plus JX equivalent to refer to the winding 1. Neglect the shunt admittance. So all the shunt branch is being ignored here. So from the short circuit, I have V1 and I have the P value. How can I proceed? to get the values of R and X. So since I have the rated power of that component, I can get I, okay, which is S divided by V. So you get the rated current for winding 1. This is the typical current that should be circulating if I'm using the transformer at its full capacity. And then I need to get R equivalent, which is P over I squared, I1 squared. I got the P value here, it's 300. And this one was calculated. It's 41.6, the rated current. Okay? So I would obtain R equivalent. Now, Z equivalent is equal to, let's say V1 is equal to ZI. Okay? I have I and I have V. I could calculate Z. So it will be 0.84. And then R plus JX equals Z, which means Z equal to radical R plus X squared. I have Z, I have R. No, this should be here. R squared plus X squared. So I could get X, okay? X is equal to radical Z squared minus R squared. Then you're done on this section. So you got R, you got X, and Z equal R plus JX. It will be equivalent to those two values. Either one is fine. Which one you write in the exam or examine is fine. But I prefer this structure, okay? The phasor representation, because I see the magnitude and the angle. It would be nice if you put them in that structure. Now, let's go to part B. So we made open circuit test. The series impedance here is being neglected. So here I removed everything in series. Then the values that I got are I2 equal to 12 and P2 equal to 200. Okay? So I would say V1 is equal to E1, which is AT E2. AT is the ratio, which I know it, 480 over 120, and V2 is the rated voltage. At first, we got the rated current for the short circuit test. For the open circuit test, we get the rated voltage, which came out to be 480. Then, using the equations, I would determine JC, YM, and BM and YM. So JC, which is, do you remember those shunt branches? Let me make them different. So we're trying now to get those JC and BM. So we said that JC is 1 over resistance. So here we need to flip V1 squared over P2 into P2 over V1 squared, okay? Because we are calculating the inverse of a resistance. So it's 200 over 480. 200 came out from the open circuit test, okay? So you made the calculation, you divide that by the rated value, it came out to be 0.00 something Siemens. YM, so normally we say V1 over I2, here he just multiplied by this ratio to reflect the referring, okay, for the current I2. Normally this would give you some Z value, but because we flipped them, we'll get the Y value, YM, okay, instead of ZM. So you make that calculation, so you'll obtain 0.06. Similar to R plus JX, we have here another set of Z. Here we have Y is equal to G minus JBM, where Y is equal to radical G squared plus VM squared. So whenever I got YM from this calculation and GC from this calculation, I can calculate BM from here, okay? And then I got GC and BM. So I put them in this equation and I get the equivalence of ym. So I think we finished this question. I know it needs some reading at home, slowly, part by part. Go over every term of those. Make sure to know what's ym, what's bm, what's gc, what's, I don't know. There are too many of them. And make sure to know the names, susceptance and Siemens and the units and stuff like that. Okay, don't calculate here ohms and stuff. 1 over ohm, mho it's called, or something like that. So, and don't forget the assignment, which is due on Monday. And it seems that everyone is doing well because I did not receive really critical questions about the homework. So it seems everyone is doing well, but no one submitted so far. So this is quite worrying.
Very long. It is, yeah, it is really long.
But it would count for like 10% of the total grade.
This one homework is 10% of the grade?
Yeah,
Okay.
because we have just 5 homeworks, and I think of giving this one more than 1 over 5 out of 40, because it's large. So work hard for that. It's equivalent to a midterm.
Okay. Yeah, that makes sense. Yeah.
So it's worth it. It's worth it. We just have 5 assignments. Otherwise, I'll make 10 assignments. So each chapter will have 2.
I thought we were gonna have one every week.
No,
That's good.
no, not one of those every week. There's a lot of work. 1 per chapter.
This is gonna be decent.
No.
I had to do this on like co-op.
No. Don't solve it. It's a first problem. No. We'll take it out.
Excuse me, Professor.
Yeah.
I won't be able to be in class next Friday because I have to drive someplace to get a drug test for the job that I accepted. So,
Okay. What's your name?
Sam Laurel, it's right here. This is me.
Okay.
Yeah, Samuel J.
Yeah,
So,
that would be.
am I still going to be counted as absent? I mean, I won't be here.
I
so-
won't send you a warning
Okay.
because it seems that you are attending. I
Okay,
sent a few
sweet.
warnings this week, maybe
Okay.
3. But
Okay.
those missed 4 or 5 sessions out of 5.
Okay.
So it's an extreme case.
All right.
Yeah, that's fine. You could go.
All right. Sweet. Is it just going to be like regular lecture? You're not going to like hand out an assignment that I'll miss or anything, are you?
I won't be solving the assignment because which day? Friday, next Friday?
Yeah, Friday. What do you have planned for next Friday? Do you know?
I ordered actually the grader to start on Monday grading,
Okay.
but I don't know. You are like 60 people in class.
Oh, no, I'm not asking. I just wanted to make sure that like I could catch up with whatever you go over on Friday is what I'm saying.
I think you would.
Okay.
You
Okay.
know,
So I
it will
won't be
be-
missing out on anything that like
and the
okay.
lectures are recorded. You could.
Okay, sweet.
But the good thing you told me that you are missing a class because of some tests.
Okay.
I had the same test today, anyhow.
Okay. So I wanted to let you know.
So
like,
I
you
won't
didn't
send
just-
you a warning.
Okay, sweet.
And then I don't see that you missed too many lectures even before, because I know the people who have too many pink blanks.
Mhm.
So it won't be.
All right, sweet. I just want to let you know.
Okay, great.
Have a good day.
You too.